On to part 3 of the twin paradox, and in this part we're going to do a quantitative analysis of what's going on, Bob's perspective versus Alice's perspective. Before we get to that, though, want to go over one more point here that I didn't emphasize probably quite enough in the earlier video clips, because some of you may still be thinking, well, it still seems symmetrical to me. In other words, Alice travels to the star and back again. That's from Bob's perspective. From Alice's perspective, she sees the star come to her, Bob go the other direction, turn around as it were, and come back to him. How do you tell the difference between those two situations? Aren't her observations the same? Shouldn't they be the same as Bob's observations? In actual fact, this is where the acceleration does come in, and that is only Alice undergoes acceleration. In other words, when you accelerate, you actually feel something, unlike constant velocity motion. So when she gets to the star and she has to decelerate, she'll feel that deceleration. Same thing accelerating back toward Bob. Whereas Bob does not undergo any acceleration or deceleration, does not feel anything. In fact, only Bob, between the two of them, can, where you can have a diagram where he has the same reference frame. He does not change his reference frame at all because he's stationary, as it were, whereas Alice does change her reference frame as we've seen. So that's where the asymmetry comes in. And certainly acceleration is involved there and deceleration. But what we've argued is that by confining it just to a very small region, the effect is such that we can still do the analysis using the special theory of relativity, as we'll see right here, and as we saw in the last video clip with the diagrams. But it certainly is true that the acceleration and deceleration is what makes Bob's situation asymmetrical, different from Alice's situation. Okay, so let's see if we can do the quantitative analysis then. It's really using concepts that we've used a number of times before, time dilation, length contraction, leading clock's lag. The three big ones there are the relativity of simultaneity of synchronized clocks. So let's see how we put this together. And Bob's analysis is pretty straightforward, as we've said before. He observes Alice travel to the star at constant velocity. The star, in his frame of reference, is 3 light years away. She's traveling at 0.6 times the speed of light. And again, we're using units such that c is 1 light year per year. And 3 divided by 0.6 is just 5 years then. Okay? And then he observes Alice's clocks. Alice is moving at velocity v with respect to him. So this is the outbound trip to the star. Ticking more slowly because it's a moving clock, time dilation. And so 1 over gamma factor, gamma being 1.25 for velocity 0.6 c. So 5 divided by 1.25 is 4 years. So he will see her clocks tick off 4 years, while his clocks tick off 5 years for the outbound trip. And then she turns around and comes right back again. So he sees the same thing happen on the inbound trip. She covers 3 light years. It takes her 5 years at 0.6 c. Her clocks tick off another 4 years. His clocks tick off 5 years. And when she gets back, he says, hey, you're only 8 years older than you were when you left, and I've aged 10 years in this case. So again, just using the concepts of time dilation there, it makes sense that Alice would be younger. The hard part again comes on what about Alice in terms of her analysis? What does she think? Well, so let's think about this a minute. Alice, in her frame of reference, stationary. She's going to see the star coming toward her and Bob receding backwards in the distance. And remember, that means there's a length contraction effect. So in Bob's frame of reference, it's 3 light years to the star. In her frame of reference, okay, so distance to the star, or really we should say the distance the star travels to get to her, right, from her frame of reference, her perspective, is going to be 3 light years over gamma. 3 light years divided by gamma, which is 1.25, and 3 light. I had 3.1 there. 3 light years divided by 1.25. When you do that, you get 2.4 light years. Ly for light years there. Okay. Now she sees the star coming toward her at 0.6 times the speed of light. So 2.4 light years divided by 0.6 c, and again c, 1 light year per year. When you do 2.4 divided by 0.6, you get 4 years. Okay, so that's how much time ticks off her clock. And again, it's consistent with Bob's observation, although his analysis of how he gets that 4 years is different. He sees his clocks tick off 5 years while she travels, a distance of 3 light years. And he sees time dilation, observes her clocks being time dilated, so it's 4 years. Whereas she sees the distance of the star coming toward her contracted to 2.4 light years, a shorter distance. And at that velocity, it takes 4 years for the star to reach her. So both of them agree Alice's clocks tick off 4 years, or really Alice's clock in her spaceship ticks off 4 years from the time she leaves until the star gets to the star, or the star gets to her from her perspective. Okay, now what about her observation of Bob's clocks? Okay, so she observes Bob's. Now we have to be careful here, because really Bob has at least 2 clocks involved that we're going to be interested in. There's going to be a clock at the star and the clock back on, we'll say, his home planet, if he's on a planet here on Earth, say. And so got one here, one there. They're both synchronized in his frame of reference. They're part of his lattice of clocks. And so in general, though, she will, wherever they are in his lattice of clocks, when Alice observes one of his clocks, she will observe the clock ticking more slowly than hers. Okay? So she observes Bob's clocks to essentially read, well, instead of saying read, let's say we'll just say to tick how many years are they going to tick? Well, again, it's the gamma factor. Her clocks tick for 4 years. So it's 4 over gamma. She sees the time dilation in his clocks. And when you do that, you get 4 divided by 1.25 is 3.2 years. Okay, and again, here's where the paradox comes in, because Alice says, okay, on my outbound trip, my clock definitely ticks for 4 years. We both take a photograph there. We both agree. My clock ticks for 4 years. But 3.2 years, I see Bob's clock ticking more slowly than mine by the gamma factor. And yet, wait a minute, what's this 5 here? Bob is saying his clocks actually tick off 5 years, not 3.2 years. We've got to be able to take a photograph at that point and get them to agree. If the clock is, both at the same point in space and take a photograph, they have to agree in terms of their analysis. And the other part of that, too, is if you just say, okay, same thing for the return trip here. Distance, the star moves away. Bob comes back again. 2.4 light years contracted. 0.6 c. 4 years, another 4 years on Alice's clocks. But she observes Bob's clocks to tick more slowly for 3.2 years. And so it would seem like she has 4 years on the outbound trip, another 4 years on her clocks, 8 years. But Bob's clocks, 3.2 plus 3.2, 6.4. And yet Bob's analysis says, no, my clocks tick off 10 years. So how can we understand that? And we showed diagrammatically last time that's an effect of her changing her frame of reference. That when she turns around, she was in a frame of reference with going this way in lines of simultaneity, parallel like this. When she changes that frame of reference, now the lines of simultaneity are different. It's a different frame of reference. And so there's a jump. It's not an instantaneous jump, but the jump occurs during her deceleration and acceleration phase. Bob's clocks tick ahead from 3.2 all the way to 6.8. And so we want to understand that now quantitatively. Last time we did it diagrammatically. We want to understand that quantitatively using some of our old friends here, if they're friends to you, maybe old enemies at this point, but using our special theory of relativity concepts and equations we've developed. So first thing to note here is, again, let's think about Bob's 2 clocks. He's got his Earth clock and he's got his star clock. And Alice can observe both of those. And let's think about this a minute, that Alice is observing on the outbound trip, or really as the star comes toward her, what's happening. Well, if both clocks, when they start off, were at 0, both of their clocks here, as the star comes toward her, we have a leading clock's lag effect. In that case, the leading clock in the star Bob frame of reference compared to Alice is the clock on Bob's planet. Okay? And that means is the star clock here is going to be ahead of the clock back at the planet. So when Alice starts out on her trip, or really when the trip starts and the star starts coming toward her at velocity 0.6 c, what that means is if Bob's clock here is at 0, Alice observes this clock to be ahead of Bob's clock on the planet. Again, leading clocks lag, so I've got two clocks that are moving this direction so compared to Alice. So Bob's clock is going to be the one lagging, and the star clock belonging to Bob's lattice is going to be the one ahead. And remember that leading clock lag factor is dV over c squared, where the d is the distance in the frame of reference, Bob's frame of reference in this case, between him and the star. And so if we just do that, that's going to be 3 light years. And velocity is 0.6 c. And divided by c squared, but remember c squared is 1. C is 1, so c squared is 1 in our units we're using. So we just get 3 times 0.6, and we get 1.8 years. In other words, when Alice starts seeing the star coming toward her from her frame of reference, and both Bob and Alice, when they start off, both their clocks are at 0 at that point, and then star starts coming towards them, Bob goes away. That means Bob's clock, which is reading 0 at that point, the star clock will be 1.8 years ahead of Bob's clock at his planet, his home planet, as it were. Okay, so let's see what that does then. So as Alice gets to the star, really again, as the star gets to Alice, the star clock is now there. Okay, Alice sees Bob's clocks tick off 3.2 years. Right, running slower than hers, but because the star clock started out 1.8 years ahead compared to the clock here, Bob's clock here, it means Alice sees it start at 1.8 years down there, then as it's coming toward her, tick off another 3.2 years, and what's 3.2 times 1.8? It's 5 years. So when the star clock gets to Alice, she observes Bob's star clock to read 1.8, because it starts out at 1.8 at the beginning of the journey over to Alice, plus another 3.2 years ticked off, and that's 5 years. Okay? And so they agree. Okay? Both of them agree, yes, Bob says, yes, my star clock there, all my clocks are synchronized as far as I'm concerned, and I see Alice travel. It takes her 5 years to get there, therefore my star clock reads 5 years. From Alice's perspective, she sees Bob's clocks, his lattice of clocks, tick off 3.2 years, and the star clock starts out 1.8 years ahead of Bob's planet clock as the star starts moving toward her with velocity v equals 0.6 c. And so she gets 5 years too. Yes, Alice says, yes, I understand why your clock reads 5 years, but it's not because you think they're synchronized. It's because from my perspective, that clock was already ahead 1.8 years, and then your clocks ran slowly for 3.2 years. But they both agreed. The photographic evidence would say 5 years for that. So now what happens, though, so that's the outbound trip. Now what happens is on the inbound trip, it's really, now we do have a mirror image type of thing, because from Alice's perspective now, okay, so the star came to her, okay, now the star moves away again, and Bob's coming back this way. As soon as that happens, we really have a change in frame of reference, but more particularly from this analysis, we have a change in the leading clock's lag factor, because now the star clock, as it moves away, is the leading clock, okay? And it's Bob's clock coming toward her that is ahead. And it's going to be ahead by this same factor, the 1.8 years, because again, it's 3 light years, Bob's distance between the star and his home planet, at 0.6c gives us the 1.8. So here's what's going on. Star comes to Alice. She sees Bob's clocks tick off 3.2 years, plus the star clock was already ahead by 1.8 years, and so when the star clock gets to Alice, 5 years. That's what she sees, and of course Bob sees that as well. Then the star clock starts moving away, and Bob starts coming this way. As the star clock starts moving away, it's still 5 years. It can't change. You know, we just looked at it. It was 5 years. So it's going to start moving away again. And here comes Bob's clock now, but this time, as they're moving this way, the star clock is going to lag Bob's home planet clock. And the difference there, again, is this 1.8 years lag time factor between the two as Alice observes it. And therefore, as the whole system moves back again, the star and Bob's home planet back toward Alice, she will again see his clock tick off 3.2 years, because hers tick off 4 years, same analysis as before, sees his clocks tick off 3.2 years, but his home clock coming back now is ahead by 1.8 years. And again, it's the change in frame of reference here. So really what happens is Alice gets to the planet and figures out, okay, 5 years. And so now maybe she's instantaneously at the planet right there. Now everything is synced up. She's actually in Bob's frame of reference. If they're stationary with respect to others, she's stationary for an instant or two at the star before she heads back again. So she says, hey, yeah, star clock is at 5. My clock is at 4. Everything matches up. Then she starts heading back again. Or from her perspective, Bob starts heading toward her. And at that instant, then, Bob's clock coming back is the clock that's ahead of the star clock. And that's where you get this going up here to another 1.8. 5 plus 1.8 gets us to 6.8. Okay, this is a 1.8 leading clock lag factor here. And then another 3.2 years tick off. Okay, so this deceleration, acceleration can be accounted for within the special theory of relativity by the effect it has on leading clock's lag. And essentially that's the change in frame of reference, that as the star comes toward Alice, it's the one that is ahead, because the leading clock is Bob in that case, moving this way, and it's behind. But then when it goes the other direction, all of a sudden, this is the lagging clock, and Bob's clock is the leading clock by that 1.8 years. Put it all together, and we see the numbers work out. In other words, that Bob, his analysis is fairly straightforward. He sees 10 years tick off. Alice has to take into account not only the length contraction effect, and not only the time dilation effect, she sees Bob's clocks running more slowly, but also the leading clock lag effect as she switches frames of reference there. And put it all together, though, and it makes sense. And yes, they've done experiments like this. I've mentioned this before, where they actually took two very precise atomic clocks, took them up on a plane, commercial airliner or the equivalent, 500, 600 miles an hour in terms of the speed, flew them around, and they had to, because of gravitational effects, they had to take into account general theory of relativity effects as well, but they took into account the special theory of relativity effects, and they did show this difference, that the moving clock, the one that traveled on the airplane and came back again, compared to the clock that was at rest, actually aged more slowly. And so one of the things we'll do next week, actually, is look at some of these effects and see how time travel might be possible, or at least a special kind of time travel. So that's the twin paradox, as I mentioned before, the most famous paradox in the special theory of relativity, but really, again, a pseudo-paradox. It seems paradoxical, but within the theory itself, it all is consistent. It works out with the principles we've established before.